Hello, everybody. All right, so today we are solving problem 1037, valid boomerang, an easy problem on LeetCode with a very interesting solution. Yeah, this is one of those problems where it's less about your knowledge of programming and more of your knowledge of another subject. So this is one of those perfect problems that kind of describes how knowing some fundamental properties of mathematical concepts can be very helpful when facing certain programming problems, especially programming problems that are associated with geometry. So the problem statement states that we are given a list of 3 points in a plane, so a plane being a two-dimensional space, so we're going to be looking at a system of 3 two-dimensional points, and we need to return whether these points are a boomerang. These points are a boomerang. So what is a boomerang? Well, okay, the boomerang is defined as a set of 3 points that are all distinct and not in a straight line. So emphasis here would be not in a straight line. So if you're given a system of 3 points and those 3 points do not form a straight line, then those 3 points are a boomerang. Okay? So I think a better way of understanding this is to look at some doc tests or examples. So in example 1, we are given the points 1, 1, 2, 3, and 3, 2. So let's just take this, move it over here, this, move it right there. That'll probably give us a good example. All right, so if we had the points 1, 1, let's use different colors just to make it, that looks terrible. Let's do red. All right, so if we have the point 1, 1, that's approximately, here, one in this direction, one up, right? We're just using a two-dimensional coordinate system. Let me put this here just for, and if we have the point 2, 3, it would be 2, 3, so something like that. And the point 3, 2, 3, 2, something like that, right? So these points do indeed form a boomerang because there's no straight line that can represent these 3 points, meaning there's no way that I can draw a straight line that intersects all 3 of these points simultaneously, right? There is no such straight line. There's a curved line, right? There's certain polynomials that will fit these points, but there's no straight line that will, right? I can draw a straight line that intersects the red and the orange point, a straight line that intersects these 2 points, but there's no single way to draw a straight line that intersects all 3 points simultaneously. And that was too much erasing. Let's do a little bit smaller here. Okay. Versus the second system where we have 1, 1, 2, 2, and 3, 3. So in this example, 1, 1, so 1, 1, 2, 2, 2, 2, and we all see where this is going, and 3, 3, 3, 3. In this example, it's clear to see that there is indeed a straight line that intersects all 3 of these points simultaneously, right? There's a single line that I can draw, which is completely straight and intersects all 3 of these points. So what can be stated about these two systems? Well, since this system here to the left does not have a single straight line that can intersect all 3 points, there is not a straight line, then these 3 points are a boomerang. So this is a boomerang. And since this system is in a straight line, then it is not a boomerang. All right. So that's the basic idea of this problem. We're just taking a set of 3 points in two-dimensional space and figuring out if there's a way where we can draw some line that intersects all three of those points simultaneously. And if we can draw a line that intersects all three of those points simultaneously, then the system is not a boomerang. If there is no such line that can intersect all three of those points simultaneously, then it is a boomerang. Okay. So let's take a look at the input into our system. So our input is points, which is a list of int lists. So we're dealing with int points. Okay, so points, for example, could be described like this. It's a list of lists where each sublist is the points, which are described by two positions, an x position and a y position. So we have x naught, y naught for the first point, x1, y1 for the second point, and x2, y2 for the third point, right? So imagine if we were looking at this first example, right? We said that the first point was at 1, 1, so that corresponds to x naught, y naught. So if we wanted to just make it a little bit clearer, this would be x naught, y naught, x1, y1, and finally x2, y2 here. Right, so we're given these points in this form, and then we visually graph it so that we can kind of see the behavior of these points and get a better understanding of what the question is really asking for. Okay, so one way to always approach a problem like this, in any coding exercise, is try to translate what you did abstractly or what you did visually into something that can be represented, in code or mathematically. Right, so what we did to figure out if these systems were a boomerang was really boiled down to finding out if the system of points formed a straight line. So what we did is we just drew a line. So that suggested that we're probably going to need to, discover what the equation of a line is and use that or leverage that to find a solution to this problem. So when we're finding out if these 3 points form a line, we try to draw a straight line, right, that intersects all 3 points. Simple enough. But another thing you could do is we'll say, if we look at the line, now this might seem arbitrary right now, but we'll see in a minute why this solution is so effective. Well, if the line that intersects the red and the yellow point is identical to the line that intersects the red and the pink point, then the system of points form a straight line, right? So if the line that intersects red and pink is the same as the line that intersects red and yellow, I keep saying yellow and orange interchangeably, I'm sorry. If those lines are identical, then the system of points forms a straight line, right? And we can see that it's true in the right case, but versus the left case. So if we follow the same logic, the line that intersects red and orange, and that got messed up, right? The line that intersects red and orange, close enough, is not identical to the line that intersects red and pink, right? They're clearly not the same. So what we need to do is find this line. So we'll call this line from y01, and we'll call this line y02 because it corresponds to the initial point and the first point, so y01, and the initial point and the second point, or the y2 third point, I guess, y02. Okay, so what we need to refer back to is then the equation of a line. So if you remember, the equation of some generic line is y equals mx plus b, where x is your input, so that would refer to maybe this axis, y is your output, your value m represents your slope, so the change from relating to your input versus output, or output versus input, and the intersection point of the y-axis. So when x is 0, where in the y-axis does intersection happen, and that will be your b value. So if we wrote these for both lines, so y01 equals m01, so the slope of this line times the input x plus b01, so the point at which this line intersects the y-intercept. Same thing for y02. y02 equals m02x plus b02. So what we're trying to figure out is, well, if y02 equals y01, then we have a system of points that form a straight line, such as, whoa, oh man, such as over here. I like how I got all messed up. How do I? It's still not right. Okay, that's good enough. Okay, yeah, that's right. So the system on the left, since the lines are not identical, they form a boomerang because they do not form a straight line, versus on the right, the lines corresponding to red and orange and red and pink are identical, so they do form a straight line and thus do not form a boomerang. Okay, so the idea here is that we have to make the comparison of y01 compared to y02. So if m01x plus b01 equals m02x plus b02. So this thing is still kind of convoluted, right? There is some simplification we could do by taking advantage of an interesting trick. So I'm going to go off on a little bit of a tangent here so that we can redescribe this system of points to simplify the equation that we derived here. So one question you can ask yourself is, when we're solving this problem, it's really about the relative distances between the points, right? The distance between x1, y1 and x0, y0, and the distance between x0, y0 and x2, y2. But it doesn't really matter where the points together are located on the coordinate plane. Meaning, it doesn't really matter where, oh no, you didn't, you're not coming with. Jesus. Take the wheel. Okay. Dude, you're killing me, man. Because I'm clicking in. That's why. I wish I had some, like, music to wait, you know? Like, elevator music to get through this awkward period. Okay. So back to the problem. If we're looking at these 3 points and the lines that describe each set of points, it doesn't really matter where they're placed as long as they're of an identical distance to one another, right? So it doesn't matter if I put it over here or over here or over here. It doesn't change the fact of which do these points form a line or do they not form a line, right? I could put it over here. It doesn't change anything as long as I maintain the relative distances between these points, right? So same thing here, right? Since this system forms a line, it doesn't really matter if I move it over here, or over here, or over here, or over here. As long as these points are at the same distance to one another, the outcome is the same, right? It still forms a line. So one thing I'm going to do to simplify this problem is move the x0, y0 point to the origin. But as a consequence, to not change any parameters of the problem or the outcome, I have to move all of the other points the same distance. So if I wanted to move x0, y0 to the origin, that means that I will also have to move x1, x0 to the left, and y1, y0 down, and x2, x0 to the left, and y2, y0 down. So what I'm really saying is, if I wanted to do that, let's move this over. If I wanted to take this system and move, oh, it's going good right now, everything down this much, the implication here would be, well, these terms are going to change, because now what I'm doing is taking x0 minus x0 and y0 minus y0. That's what moves the red point to the origin. And I'm taking x1, y1 minus minus. No, let's do it. That's fine. All right, trying to get too tricky. Okay, x1 minus x0 and y1 minus y0. Here I'm doing x2 minus x0 and y2 minus y0. And the idea here is I'm not changing the nature of this problem. I'm just reorienting it, right? I'm putting it in a different position because it makes the lines that describe y01 and y02 easier to solve, right? But it doesn't change, the fact here is it doesn't change any part of the system, right? It's still the same problem. It's just in an easier to solve orientation, right? Same thing here. I'm not going to draw it all out, but if I was to move this down, it doesn't change the fact of which do these 3 points form a line or do they not form a line. And that's the point I'm trying to get across. So why did we take all this time to reorient this system of 3 points in this fashion? And the answer to that question is, well, what are B01 and B0, not this again, and B02 now that we've reoriented this system? All right, well, B01 and B02 are the value or the y value of which the line intersects the y-intercept. And we can see here obviously that we intersect y at 0, right? At this point 0, because these values will resolve to 0, 0. So this implication there is going to say, well, then this is 0 and this is 0. So then if m01x equals m02x, then the system points form a line, or we can cancel out these x's. If m01 equals m02, then the system of points form a line. Okay, so we basically have the solution now in a way, but the problem is that we're not given, two slopes, right? This is what these m values represent. We're given a system of points, so we need to find the slope from the system of points. So if you remember going back all the way to equation of a line, the slope equals the slope from A to B, make sure I'm doing this right, equals YB minus YA over XB minus XA. So if we wanted to find what the slope was associated with Y01, we'd say, okay, well, we can just use these 2 points. So we could say M01 equals y1 minus y0 minus 0 over x1 minus x0 minus 0, and m02 equals y2 minus y0 minus 0 over x2 minus x0 minus 0. Or, and if these things are equal, meaning if y1 minus y0 over x1 minus x0 equals y2 minus y0 over x2 minus x0, then this system forms a straight line. Now this is fine, like you could technically use this as your solution, you could convert this to code, but you're going to have to account for some issues that might arise when x1 equals x0 or x2 equals x0 because the quantities are the same. So when you subtract them from one another, you're going to get 0, and then you're going to see that 0 is in the denominator, can't divide by 0, the program's going to crash. So then to account for this, you're going to either have to create like a try-catch block situation or add a few conditionals, but it makes your code a little bit messier. So something you can do to simplify this is to do some algebra on the system so that there is no values in the denominator, which can simplify the problem. So that's what we're going to do now. So if we were to simplify this problem, so y1 minus y0 times x2 minus x0 equals y2 minus y0 times x1 minus x0. And just distribute all these terms. So just bear with me while we do all this. y1, x2 minus y1, x0 minus y0, x2 plus y0, x0 equals y2, x1 minus y2, x0 minus y0, x1 plus y0, x0. Something nice that can be seen here is that these y0 terms actually cancel, which is kind of cool. Now I'm going to move everything to the left side, and it's going to look a little weird because I'm going to be just moving terms to get kind of a nice looking pattern. So put this, so x0 y2 minus x0 y1, so that's these two terms, okay, plus x1 y0 minus x1 y2 plus x2 y1 minus x2 y0 equals 0. Then if we factor out x naught, y2 minus y1 plus x1 y0 minus y2 plus x2 y1 minus y0 equals 0. 2, 0, 1, 1, 0, 2. All right, and this is the solution here, right? Because if this set of these points, which were given, right, in our initial problem, we know that we're given these values, we can just plug those values into this, and if they equal 0, then the system forms a straight line and therefore is not a boomerang, or if they do not equal 0, then the system does not form a straight line and these points are a valid boomerang. One last thing I'm going to do to kind of simplify this problem to make it just a little bit nicer is treat it as a summation from I equals 0 to 2, including 2, of x to the I times y of I plus 2, let's see, 2, 0, you got 2, 0, 1, so call that a mod 3, minus y, be the same mod but different shift, so y of I plus 1 mod 3. Yeah, 1, 2, 0, okay, equals 0. So there you go, there's the solution. So if this equals 0, then straight line, so not a boomerang. And if this term, gosh, this iPad, you know, it's just awesome. This term not equal 0, then is boomerang. All right, so if we wanted to convert this statement into code for our solution, well, we're going to want to take the sum of something with I, so we might need more space, I don't know, for I in range 3, because we're going from 0 to 3, or 0 to 2, so this is excluding 3, so this will sum through the values I, 0, 1, and 2. All right, we're going to want to multiply x to the I. So how do we get x to the I from our input points? So it can be seen. That actually worked? That's cool. Okay. If we wanted xi from points, we would do points at I, which would give us xi, yi. So if we did points I at 0, that would give us x to the I. Okay, so then here we're going to put sum of points I 0 times, and I definitely did not give myself enough room. Always do that. Times, how would we get y term? So I want yi plus 2 mod 3. So if I wanted the y term, I would just do points at I of 1. Since I will give me xi, y, this will give me y at I. Okay, so if I did points at I plus 2 mod 3, 1 minus points I plus 1 mod 3, 1 for I in range 3. Now the cool thing about this is that we don't actually have to compare it to anything, because just by the nature of Python truth and false values, since the funny thing here is that when we evaluate this term, if this term equals 0, then it's not a boomerang. But in Python, 0 evaluates to false. So when this thing gets evaluated to 0, it'll return false, which is right because it isn't a boomerang. Versus when we evaluate the system and it doesn't equal 0, well, then that means that the system of the points do not form a straight line, so they are a boomerang. But since they also don't equal 0, Python will evaluate any integer value that doesn't equal 0 as a truth value. So this set of points, we just return this, it'll evaluate the solution. So this is the solution you would type into LeetCode to get the correct answer. And if you are still confused, we have a little example here. So for example, if we were looking at these 3 points, let's move x0 over here. x2, x1, we're saying that the slope is really what defines whether these 3 points form a straight line. So this set is a valid boomerang because the slopes, as you can see, are different. Versus when we move it here, you can see that, okay, these 3 points do form a straight line and their slopes m01 and m02 are the same. Kind of cool thing here is you can see like how close 2 lines are from being straight. Like these are almost form a straight line. Versus here, right, I'm just approximating here, they do. Right, and this works in all orientations. Right, if we go here. Right, so this is just a cool way of showing that how the slopes interact when we're dealing with these points. Anyways, I hope this helped. Thank you for watching my video. Have a good